Hello, this is Dr. Hanaa Assil and this is Unit 5, January 2024 of the Pearson Edexcel International A-Level Chemistry. Let's take a look at the questions and discuss the answers. So the first question says the apparatus can be used to measure E naught of the cell for the reaction shown. So we have chromium 3 plus zinc to give chromium 2 plus zinc 2 plus. Which electrodes are used for this cell? So the one on the left is the one that has the zinc 2 plus, and that means this is the zinc 2 plus half cell. Zinc is a solid, so that would be the electrode 1. So my electrode 1 is zinc. Now, looking at the half cell on the right, we have in solution chromium 2 plus and chromium 3 plus. So my electrode 2 has to be platinum. If both are solutions, then the electrode is platinum. So that is the answer. A student wishes to measure the standard cell potential of this cell. The right-hand cell requires chromium 3 plus and chromium 2 plus ions. What mass of the chromium 3 sulfate salt must be dissolved in 1 decimeter cubed of deionized water to give the concentration of chromium 3 plus ions that is required to measure this E cell? Now, remember that to measure the E cell, I need 1 mole per decimeter cubed of the chromium 3 plus. But then the idea that we're starting with chromium 3 sulfate, now when the chromium 3 sulfate breaks up, 1 mole of the salt will give 2 moles of chromium 3 plus. So if I want to end up with 1 mole per decimeter cubed of chromium 3 plus, then I need to have actually a 0.5 mole per decimeter cubed of that salt in order to end up with 1 mole per decimeter cubed of chromium 3 plus. So the question is, what is the mass that I need? Now, of course, to get the mass, I need the molecular mass. So we calculate the molecular mass of the salt. We have 2 chromiums plus 3 sulfurs plus 12 oxygens plus 18 water. Each of them is 18. So the total MR is 716. Now to have a solution of 0.5 mole, the mass is number of moles times the MR. So the mass we need is 358 grams. What can be deduced from the fact that for this reaction the E cell is positive? So if we say that the E cell is positive, what does that tell us? You should know that the E cell is proportional to the natural log of K, and it is proportional to delta S total. So if we say that the E cell is positive, then both of them should be positive. We know that the delta S total is equal to R ln K, and we are saying the E cell is positive. That means both of these values should be positive. Question 2 says they have equations for a hydrogen-oxygen fuel cell in alkaline solutions are these. The equation for the overall cell reaction is what? Remember that we have reactions for the hydrogen-oxygen fuel cell in alkaline electrolyte, and we have reactions in acidic electrolyte. But for both of them, the overall reaction is what? The overall reaction is hydrogen plus oxygen to give water. That is the overall reaction. Calculate E cell for the reaction occurring in the hydrogen-oxygen fuel cell under alkaline conditions. So these are the equations that we have under underlying conditions, and these are the information that we were given at the beginning of the question. And we should know that, well, that first reaction to give hydrogen, we need to invert it because we're starting with hydrogen and we're going to end up with water. So we need to invert the sign of the E note. So the E note for that was a negative value. When we invert the reaction, we invert the sign, and that means the overall E cell for this fuel cell is the total of the two E notes, which is a total of plus 1.23 volts. Which successive ionization energies are most likely to be those of a transition element? Now, when we have successive ionization energies for a certain element, we look at where we have a sudden jump or a huge jump in the ionization energy. So if we look at the sequence we have in A, we have for the transition metals, you know that the transition metals are the parts in the middle of the periodic table, and they end up with d orbitals in the end. Now, if we are looking at the choices in A, where is a huge jump? We have a huge jump after the third ionization energy, and that means that is an element in group 3. For the choice in B, there is no huge jump anywhere, so that must be the transition element. The one in C has a huge jump after the fourth ionization energy, that means it's an element in group 4. The choice in D has a huge jump after the third, that means this is something in group 3. But where we do not have a huge jump from one ionization energy to the next, that is probably the transition element. Which sequence shows the ions in order of increasing strength as a reducing agent? Okay, if we look at the data booklet, the order in which they are arranged so that the ones on top are the stronger reducing agents. The ones down are weaker reducing agents or more likely to be reduced. So if we look at the choices that we have, where are the choices? We have chromium 2+, V2+, iron 2+. The ones on the top of the table would be the stronger reducing agents. We're asked to arrange them in order of increasing strength. That means the iron 2+ would be the lowest in reducing agents, then the V2+, and then the chromium 2+ would be the stronger reducing agent. This question concerns the chemistry of copper. In the reaction sequence, substances PQ, R, S, T, and U contain copper in various oxidation states. And the question first is, what are the electronic structures of 3 copper species? So we're looking for the electronic structure for the copper metal, the copper +1, and the copper 2+ ions. So if you look at copper, copper has atomic number 29. That means the distribution would be 3d10, 4s1. Remember, we're supposed to fill the 4s before the 3d. So actually it should be 3d9, 4s2, but we said the 3d needs only one more to be filled. So we take one from the 4s and put it into the 3d, and that means the configuration for copper is actually 4s1, 3d10. So that is the copper metal. So my answer is C or D. Now, when we remove one electron, we're going to remove it from where? Remember, when we remove electrons, we remove them from the 4s before the 3d, because that's the 4th energy level. So the copper +1 is actually argon with 3d10. Now, copper 2 plus, we're going to take the next electron from the 3d10, so that would be the 3d9, so that would be the correct answer. Which rows show the substance with their correct oxidation state? So this was the flow chart that we were given, and we're looking for where do we have copper metal, copper 0, where do I have copper plus 1 and copper plus 2. So if we look at this, P is a blue solution, and you should know that the blue solution is when we dissolve the copper 2 plus in solution, it forms a blue solution. So all of these are copper 2s. Now, when we react it with potassium iodide, we are being told that it gives CuI, and that means that is Cu with plus 1. And if we add the aqueous solution X, then S is copper plus 1. Now, when we add sulfuric acid to that, it says it gives T, which is a pink solid. And you should remember, if we're working with copper ions, then if something precipitates out as a pink solid or a reddish brown solid, that is our copper. So the copper solid is T. Now, what is copper 1? Copper 1 is the S. And copper 2 can be P. Do we understand that? Aqueous solution X. What is X? We are told that we have P, and we said P is copper 2 plus. We put sodium hydroxide. It gives a pale blue precipitate. Now, we are told that if we add aqueous solution X, it gives a dark blue solution. When do we get a dark blue solution with copper ions? This is when we add what? This is when we add aqueous ammonia. Then the copper forms a complex with 4 ammonias and 2 water, and that is the dark blue solution that we get. So solution X must be ammonia. The diagram shows the skeletal structure of thiobromine, which has a bitter taste and is found in chocolate and tea leaves. Which of the functional groups listed is not present in the structure? Well, let us take a look. Do we have an alkyl group? Yes, we have an alkyl group. That's the CH3 attached to the N on the right. Amide groups, we have 2 amide groups on the left. Amine, that is the nitrogens that we have there, we have 2 amine groups. Do we have a ketone? We do not have a ketone. Those double bond O have a nitrogen next to it. These are amide groups, not ketones. Peptides are short chains of amino acids linked by peptide bonds, or what we call amide bonds. How many different types of amino acids have joined to form this polypeptide? Okay, so we look at the breaking of the amide bonds. That's where one unit was attached to another. So if we look at this, we have these units breaking off at the amide bonds. The ones that are similar are counted all as 1. So actually, we have a total of 5 different amino acids. We have 4 of them are similar and the rest are different. So they are a total of 5 different amino acids. Then this question says, which shows the structure of the amino acid lysine as a solid and in solution at high pH? You should know that for amino acids, we said when it is in solution, it is in the form of a Zwitter ion. Zwitter ion means the acid part is COO minus and the base part is NH3 plus. So that is in as a solid or at the beginning. So as a solid, which one do we choose? It's either B or D. Then in solution at high pH, we have at high pH the Base is as it is, the NH2 is NH2, but the acid part is, this is in base, so the acid part is COO minus, so the answer is B. Question 9 says a dipeptide has the molecular formula that has 7 carbons, 12 hydrogens, and so on. The dipeptide is hydrolyzed to form 2 amino acids. One of the amino acids produced does not have a chiral center. What is the structure of the other amino acid which does have a chiral center? So we have an amino acid with, or a dipeptide with 7 carbons. Now we're going to break it up into 2, hydrolyzing of the dipeptide. We want one that does not have a chiral center, so that is probably that part on the right. This would not have a chiral center, and then the other part would be something like this with how many carbons? 5 carbons. So that is the part we're trying to identify. What is the structure of that part? It has a chiral center, and which part of that can be possible? First of all, A is wrong. We don't have sulfur in our molecular formula anyway, so A is wrong. Then that part has to be something that has 5 carbons. Well, D has a total of 6 carbons, so that D is off. So it's either B or C, and the difference between B and C is actually in the number of hydrogens. So if we remove that part on the right, then we should have the number of hydrogens present in C. B will have the wrong number of hydrogens. Question 10. The aroma of strawberries is due to a number of volatile compounds, including the 4 isomeric esters shown. So these are esters. Which of the esters have 5 peaks in their carbon-13 NMR? Well, let's see. Which one has 5 different carbons? So, looking at P and Q, all the carbons are different, so we have a total of 6 peaks for that. R and S have 5 carbons, so it is R and S. Which of the esters will not have a doublet in its high resolution proton NMR? Now, to have a doublet, we need a neighboring carbon that has one hydrogen. A neighboring carbon that has 1 hydrogen would give a doublet. Which of these would not have a doublet? Which of these would not have a carbon with 1 hydrogen, so that the other protons on the other carbon will give a doublet? So all of these have a single hydrogen on the carbon that would cause a doublet in the neighboring peaks, except P. Which of the esters could rotate? So these were the esters we were given. Which of them would rotate the plane of polarized monochromatic light? Of course, to rotate the plane of polarized light, we need to have a chiral center. So the question is, which of these has a chiral center? So this is the one that would have a chiral center. The others do not, so it is Q only. Question 11. The formula of 3 synthetic polymers are shown, which are made by addition polymerization. So where do we start? Addition polymerization means I started with an alkene. So X would start with this kind of monomer, Y would start with this kind of monomer, but Z would not have an alkene as monomer. This was done by condensation polymerization. So the ones that were made by addition are X and Y. Question 12 says, sodium thiosulfate can be used to determine the concentration of an iodine solution by titration using starch indicator. 5 grams of sodium thiosulfate was dissolved in deionized water. The solution made up to 250 in a volumetric flask. Now, the volumetric flask has an uncertainty of plus or minus 0.25 centimeter cube. What is the minimum uncertainty of the balance required to match the uncertainty of the volumetric flask? So we want the same uncertainty as the volumetric flask, and the question says assume two weighings are needed. So we're going to use we're going to weigh using the balance twice. So if we have 5 grams in 250 centimeter cubed of volumetric flask, and we're told that the uncertainty is plus or minus 0.25, then the percent uncertainty of the result is the 0.25 over the 250 times 100. And of course, the volumetric flask is read only once. So the percent uncertainty for this is 0.1. Now we want the same for the balance. Now, remember we said we're going to use two readings, and that means the uncertainty that we're trying to get will be twice. So if we said the uncertainty is something, then we're reading it twice, then it is 2x. Over the reading that we want to read, what do we want to read in the balance? We want to read 5 grams times 100, and I want the total of that to be 0.1. What is x? When you solve for x, it is plus or minus 0.0025. Okay. The titration was carried out with sodium thiosulfate in the burette, and starch was added just before the end point. Remember, when we're titrating with sodium thiosulfate, what we do is we have iodine in the flask, so we are starting with the flask as a reddish brown or brown solution. As we add the sodium thiosulfate, the iodine is being used up, so the brown color becomes fainter and fainter and fainter until it is about yellowish. Then we add the starch just before the end point. So what would be the color of the solution at the end point? So at the end point, what we had is, when we added the starch, it became dark blue black. Now adding a few drops of sodium thiosulfate, once the iodine in the flask has been used up, it turns colorless. In 1865, Frederick August Kekule suggested a structure for benzene which consisted of alternating single and double carbon-carbon bonds. So that was the Kekule structure. However, modern analytical techniques indicate a structure in which the electrons are delocalized over the 6 carbons. So we have the delocalized structure. Explain how the results of X-ray diffraction experiments on benzene suggest a delocalized structure rather than the Kekule structure. They found, why did they decide that we have a delocalized structure? It was because when we did the X-ray diffraction experiments, they found that all the bonds are the same length. So if we had the Kekule structure, that wouldn't be the case, because the double bonds are supposed to be shorter than the single bonds. So the fact that all the bonds are the same length means we do not have the Kekule structure, we have the delocalized structure. The compound 1,2-dichlorobenzene exists as only one structure, 1,2-dichlorobenzene should have this kind of structure. So if we have the Kekule, in which we have alternating double and single bonds, then we should have an individual compound that has a double bond between the 2 chlorines and another different compound that has a single bond between the 2 chlorines. Now, what they found is actually we have only one. We do not have 2 different 1,2-dichlorobenzene. Now explain how this supports the delocalized structure. Of course, this is because the isomers in which one has single bond between the carbon atoms and the other has a double bond has not been found. So this indicates that all the bonds are equal. So instead of having two different compounds, we have only one compound, and that means the delocalized structure is what we have. State how the enthalpy changes of hydrogenation for cyclohexene and benzene provide evidence for the delocalized structure. Now, the enthalpy change of hydrogenation of cyclohexene, which is a structure that has only one double bond, is minus 118. Now, our benzene ring is supposed to have 3 double bonds. So if we have individually 3 separate double bonds, then the delta H of hydrogenation for benzene should actually be 3 times the delta H that we have for cyclohexene. Actually, the value is, so the value should be, if it is 3 times of minus 118, it should be minus 354, and the actual delta H of hydrogenation given is minus 205, which is smaller, much smaller, or much less exothermic than expected if we are counting for 3 carbon-carbon double bonds. So the benzene is supposed to have 3 carbon-carbon double bonds. Cyclohexene has only 1. So if the 3 are different, we should multiply by 3. What we actually have is much less than the expected value for 3 double bonds. Describe the structure of benzene in terms of atomic orbitals involved, the bonds formed, and the delocalized electrons. So we should know that the benzene ring is made up of 6 sigma bonds, and we know that the sigma bonds are due to overlap of the p orbitals head to head. And we have the pi bonds, which are delocalized. They are formed by the overlap of the p orbitals side by side over all the 6 carbon atoms. So that is the delocalized structure of the benzene ring. N-phenyl ethanamide, historically used as a painkiller, can be synthesized from benzene as shown. So we are given this flow chart starting from benzene. We want to make N-phenyl ethanamide. Concentrated nitric acid reacts with a secondary agent to produce an electrophile. Then the electrophile reacts with benzene to form nitrobenzene. Identify by name or formula the secondary agent. So we are told that the first step in the synthesis is we're trying to form nitrobenzene from benzene. What do we react with benzene to give nitrobenzene? We're going to react concentrated nitric acid and sulfuric acid, concentrated sulfuric acid, because both, when they react, they form the electrophile, and the electrophile here is the nitronium ion, or the NO2+. So when we're reacting benzene with concentrated nitric and concentrated sulfuric acids, we form the nitrobenzene because they're going to react with the electrophile, which is the NO2+. Draw the mechanism for this reaction between the electrophile and the benzene to form nitrobenzene. So we're starting with benzene. We're going to react with the nitronium ion, which is the NO2+. So you can write it NO2+, or you can draw it like this. And of course, the first step is the electrophilic addition. Electrons coming from the delocalized benzene ring attacking the positive on the nitrogen. This joins the NO2 to the benzene ring, and then we need to give up the electrons between the benzene ring and that hydrogen in order to have the nitrobenzene product. Identify by name or formula the reagent required to convert the nitrobenzene into phenylamine. So now I have nitrobenzene. What do we react with to form phenylamine? Of course, you should know that this is with tin and concentrated HCl. This changes the nitrobenzene into the phenylamine. What type of reaction is this? When we change NO2 to NH2, this is a reduction. Okay? In the final step of the synthesis, phenylamine reacts with either ethanoyl chloride or ethanoic anhydride. And we're given the two equations. Ethanoyl chloride is more reactive, and we should know that acyl chlorides are much more reactive than carboxylic acids, and we're told than ethanoic anhydride. The hazard symbols are shown. Okay, so the question says, assess the advantages and disadvantages of the use of ethanoic anhydride rather than ethanoyl chloride for this reaction. Consider the hazards associated with the reactants and products and the atom economy of each reaction. So let's take a look at this. What do we have? From the hazard symbols, we can see that ethanoic anhydride and ethanoyl chloride, they are both flammable, corrosive, irritant, but ethanoic anhydride is also toxic, so that's a disadvantage. Now, when we look at the products, what is happening? Ethanoyl chloride gives HCl, the molecular mass is 36.5, while ethanoic anhydride gives the ethanoic acid with a much larger MR, so the ethanoyl chloride would give a higher atom economy. You know how to calculate atom economy? Atom economy is the MR of the required product, which in this case is N-phenylethanamide, over the total. So if the total of the other product, the MR of the other product is larger, then the atom economy is smaller. So HCl, the one that gives HCl, is higher atom economy. It also reacts faster. We were told that ethanoyl chloride reacts faster, but that means that it may cause side reactions. So that could be another disadvantage of the ethanoyl chloride reaction. What happens if we're looking at the hazards of the products? Now, the products are either ethanoic acid or hydrogen chloride. Now, what is the difference in the hazards? The products in both cases are corrosive, but the HCl is also toxic, while the ethanoic acid is flammable. Okay, so you need to write the answer in correct expressions. Okay. The overall yield for the synthesis of N-phenylethanamide from benzene was found to be 35.2%. So we are told that the yield is 35.2. Calculate the minimum volume of benzene required to make 10 grams of N-phenylethanamide. So the N-phenylethanamide, if we take a look at the formula, you will see that this is the formula of the N-phenylethanamide. So we can get the MR of that, and remember that the overall yield of this reaction is 35.2. So when they say that we got 10 grams of N-phenylethanamide, the 10 grams is due to the 35.2% yield. Now we want what would give 100% yield. So that means we should have obtained 28.4 grams if it was 100% yield. Now, based on that, we need to calculate the volume of benzene required. So, number of moles of the N-phenylethanamide is the mass over the molecular mass. So, that's number of moles of the product. That would be the same as number of moles of benzene. Now, MR of benzene is 78, so the mass is the number of moles that we got times the MR, which is 16 grams. So we're supposed to start with 16 grams, 16.4 grams, but we're required to calculate what? The volume. Well, we know that density is mass over volume, so I can get the volume from that using the mass and the density given. So that means that the volume we should get, and the density is given in gram per centimeter cubed, so the volume is in centimeter cubed. Another painkiller, paracetamol, can be synthesized from phenol in a similar sequence. Phenol is nitrated by dilute nitric acid. So we're starting with the same idea of the benzene ring being nitrated. Explain why the nitration of phenol requires much milder conditions than the formation of nitrobenzene. So when we were trying to add nitro group to the benzene ring, we said we're going to react it with concentrated nitric and concentrated sulfuric. But for phenol, we only need to react it with dilute nitric acid. This is because, of course, in the phenol, we said the phenol is more reactive than benzene, because in the phenol, the lone pair of electrons on the oxygen overlap with the delocalized pi cloud of the benzene ring, and this increases the electron density of the ring, so it is more likely to do electrophilic addition. Question 15 says, gingerol is a compound found in fresh ginger that activates spice receptors on the tongue, giving raw ginger a hot taste. The skeletal formula of gingerol is shown. Give the molecular formula of gingerol. So, how many carbons, hydrogens, oxygens in the molecule? So looking at it, you can see that this is a total of C17H26O4. The OH group is shown attached to the carbon chain by a wedge-shaped bond. Can you see that? The OH is attached with a wedge-shaped bond. So just why the bond between the carbon chain and the OH group is shown as a wedge. What does that mean? Remember that if it is drawn as a wedge, this actually means that that bond is pointing towards us. If it is a bond with dotted lines means the bond is pointing backwards. So this wedge is an indication of the three-dimensional arrangement of the OH on the chiral carbon atom. Cooking fresh ginger converts the gingerol into something else which is less pungent and has a sweeter flavor. This compound can be formed in a four-step synthesis from coniferal alcohol. Step 2 in the synthesis involves a Grignard reagent, while steps 1, 3, and 4 are redox. The synthesis is shown with structures of the intermediate compounds. Complete this four-step synthesis and include in your answer completed structures of the intermediate compounds, reagent. So basically what we're trying to do is we're trying to change that coniferal alcohol into Zingerone, and we're given the different steps. So step 1, what should we do first? Remember, we have an OH at the end of that side chain. We need to do an oxidation reaction, and then we were told in step 2 we should use Grignard. So we're trying to change this alcohol part, so that is an oxidation reaction with potassium dichromate, concentrated HCl, and I want to end with an aldehyde. So I need to say that we're doing distillation in order to end up with an aldehyde. So that is the first step, and then this aldehyde I can react with Grignard. So we're starting now with the aldehyde in step 2. How do we do Grignard? Remember that the final product that we want we need to add that methyl group at the end. There is a methyl group that I should add to this aldehyde that we have. So in order to do that, we do a Grignard that has methyl. So methyl bromide plus magnesium in dry ether, this gives CH3MgBr. Then we do dilute HCl. This would add the extra carbon that we need, and it will change the aldehyde part into an OH. Now what are we supposed to do? So we're starting now with this in step 3. Now how do we try to get to the product? In the product, we need another oxidation so that we change that OH to a ketone. So in this case, we want potassium dichromate, concentrated sulfuric acid, and reflux. So that gives me the ketone. And then how do I change this ketone to that final Zingerone? What is the difference between them? Is removal of that double bond. So to remove that double bond, we do hydrogenation with hydrogen and nickel catalyst. That gives the final required product. Okay, then question 16 says a Latimer diagram for a chemical element is a summary of the standard electrode potential data for that element. In a Latimer diagram, the form of the element with the highest oxidation state is on the left, with successively lower oxidation states to the right. So in this case, we're talking about manganese, and we're starting with MnO4 minus, which is the manganese in the +7, so that is the highest oxidation state, and successively until we end up with manganese metal, which is in the 0 oxidation state. A Latimer diagram for manganese at pH equals 0 is shown, and these are the different electrode potentials. Now, the diagram shows that the standard electrode potential for the reduction of MnO4 minus to MnO2 in acidic conditions is plus 1.69. And we have the equation. Justify the assignment of the oxidation state of +5 to H3MnO4 using oxidation numbers. So we're starting with H3MnO4, and we're required to determine what is the oxidation state of manganese. You should know how to get oxidation states. Each hydrogen is +1. We have 3 of them, so that's +3. We don't know what is manganese. The oxygens, each of them are -2. We have 4 of them. And overall, we don't have any charge, so the overall is 0. Calculating for X, the oxidation state of manganese in here is +5. Write an equation for the reaction of H3MnO4 in acidic solution to give ions containing manganese 6 and manganese 4. So we're starting with H3MnO4. Looking at that, H3MnO4, on going to the left, it gives HMnO4 minus, which is manganese in the +6 oxidation state. Going to the right, this is manganese in the +4 state. So we're starting with MnO4 3 minus, and we're being told that this is in acidic conditions, so +H+. And we're told that it is going to give manganese in the +6 and manganese in the +4. Of course, if I have H+ before the arrow, I should have water after the arrow, and then we try to balance. How do we balance here? We have 2 manganese after the arrow, so I need 2 MnO4 3 minus, and then we balance the hydrogens and the charges. This is the overall balancing of the equation. Deduce whether or not this disproportionation reaction is thermodynamically feasible by calculating the E naught. So we already have the E cells given from MnO4 3 minus to MnO4 2 minus. We're giving that it is minus 1.28. This is because we're going to flip the sign from the information given on top. So on the top it's given plus 1.28, but that's if I'm going the other way from MnO4 2 minus to MnO4 3 minus. I want it flipped, so I flip the sign, so that is minus 1.28. And from MnO4 3 minus to MnO2 we're given on top there, it is plus 2.9. So we calculate the E cell. The E cell, when you add this up, it is plus 1.62. The E cell is positive, and therefore the reaction is feasible. Okay. Then the second part says, before use in titration experiments, potassium manganate solutions must be standardized. One method uses ethane diuate ions to find the exact concentration of the manganate ions. 250 centimeter cubed of a standard solution contained 1.915 grams of sodium ethane diuate. A potassium manganate solution of about 0.02 mole per decimeter cubed was standardized using this solution. Excess sulfuric acid was added to 25 centimeter cubed portions of potassium permanganate, which was titrated with the sodium ethane diuate, and the mean titer was 22.95 centimeter cubed. And we're given the relevant ionic half equations. First, state the color change at the end point of the titration. So, what are we titrating? We have, in the flask, we have 25 centimeter cubed of potassium permanganate. And of course, potassium permanganate is purple. So, that's what I'm starting at the beginning of the titration. Now, by the time we add the sodium ethane diuate, the purple color has been used up a little bit, so we're left with a pink color. Now, once all the permanganate is used up, the next step, next drop from the ethane diuate will remove the color completely. So at the end point, actually, we're changing pink to colorless. Don't say purple, because we've been titrating it, we've been adding ethane diuate. So the purple color that we start with at the very beginning has been diluted or has been removed step by step until near the end point it is actually pink, not purple. And then once all the permanganate has been used up, it turns into colorless. Then the question says, calculate the accurate concentration of potassium permanganate. So, what were we told so far? We were told that we had 250 of the standard solution containing 1.915 grams of the sodium ethane diuate. Then we added excess sulfuric acid to 25 centimeter cube potassium permanganate in a flask. And this was titrated, and we needed 22.95 centimeter cubed of the solution that we're titrating with in the burette, and we're given the ionic half equations involved. So, what's the first thing we should do? We should get the concentration of the sodium ethane diuate that we're using. So from the information that we have, we can get number of moles in the 250. Number of moles is mass over molecular mass of the ethane, sodium ethane diuate. This comes out to this number of moles, and we can get the concentration of that solution. The concentration would be the number of moles over volume. So this is the concentration of the sodium ethane diuate in the burette that we are using for titration. Now, we used 22.95 centimeter cubed of that, so we can get number of moles of the ethane diweight. That would be the concentration times the volume used. So this is the number of moles of the ethane diweight. And then we look at the equations. And when we look at the equations, these are the overall equations from what he gave us. You should be able to balance them and multiply through so that the number of electrons are the same. So this is the final relationship between the number of moles. So if we have 25 centimeter cubed of the potassium permanganate, and this is the number of moles of the ethane diweight, then from the equation there I can get the number of moles of the potassium permanganate. The number of moles is a 2:5 ratio. So if I have number of moles of the ethane diweight, then the number of moles of the permanganate is that. And then we can get the concentration of the permanganate. That would be the number of moles over the volume used, which was 25 centimeter cubed. Again, in all of these equations, please do not forget to divide by 1000. So this is the concentration of the potassium permanganate solution. A second titration carried out without the addition of sulfuric acid resulted in the formation of a brown suspension. Explain how the value of the mean titer would be affected, if at all, by the reaction that forms this suspension. So we are doing the reaction with the sulfuric acid. Without the sulfuric acid, it forms a brown suspension. What is the brown suspension? The brown suspension would be the manganese dioxide that is formed. So this forms a brown suspension. Now, how does this affect the value of the mean titer? If we look at the change from manganate to manganese 2+, this needs 5 electrons. To change from the manganese 7 to manganese 2, so that's 5 electrons. But to change from manganese 7 to manganese 4, that's only 3 electrons. In order to change Mn in the +7 state to manganese in the +4 state, this is the one that forms manganese dioxide. So we need less electrons, so a smaller titration volume will be required. Question 17 says transition metal compounds can form a number of different types of isomerism. Hydration isomerism is where different numbers of water molecules act as ligands. The name of chromium 3 chloride is given to several chemical compounds with this formula. So this is chromium 3 chloride, but we have different numbers of water molecules acting as a ligand. This is including a number of hydration isomers. Anhydrous chromium 3 chloride is violet, which can react with water to form either the one with 1 water, so that is a pale green, and another one with 2 water of crystallizations, that is dark green. First question says, explain why the different isomers have different colors. Remember, if we have different ligands, the compound has different colors. Why is that? Remember that the color of the transition metal complex is due to the fact that when we have ligands, the 5d orbitals, which are supposed to have the same energy, they should be of equal energy. When there are different ligands, the 5 orbitals split so that 2 of them have higher energy than the other 3. Now, when light is passed through, the electrons in the lower energy levels absorb lights of different wavelengths in order to jump to the higher d orbitals. Now, if we have different ligands, then the energy gaps between the d orbitals are different, and that means the electrons will absorb light of different wavelengths in order to jump to the higher d orbitals, and so different light wavelengths will be transmitted, and that is why they would show, or they will appear with different colors. You are provided with 3 equimolar solutions of the 3 isomers. So just how you would quantitatively determine the relative numbers of free chloride ions in the 3 isomers. So we were told that we have 3 different isomers with different amounts of free chloride ions. So the first one, which is violet, has 3. The pale green has 2, and the dark green has 1 free chloride ion. Now, how do we determine the relative numbers of the free chloride ions? Of course, in order to do that, first of all, we need to put equal volumes of the solutions into 3 flasks. And then, how do we test for chloride ions? You should know that if I add equal volumes of silver nitrate solution, the chloride ions give white precipitate, and the amount of precipitate obtained is relative to the number of chloride ions. So we're going to filter that precipitate, dry, weigh, calculate the number of moles of silver chloride formed, and from that we can determine how many chloride ions there were in each of these. Complexes can exhibit both cis-trans and optical isomerism. The cis and trans isomers of diamine dichloroplatinum are commonly known as cisplatin and transplatin. In chemotherapy medication, it is the cisplatin that is used to treat a number of cancers, including testicular cancer, breast cancer, while transplatin has no beneficial effect against cancer. The cis isomer is effective because it binds with the deoxyribonucleic acid, which is the DNA molecules, in the cancerous cells through adenine and guanine groups that are present on the DNA. This interferes with the replication of the cell and results in its destruction. So we are told that the cisplatin, we know that cisplatin is the one that is used in chemotherapy medication, and this is because it binds to the DNA through adenine and guanine groups, and this stops the replication of the cells and results in its destruction, while the trans will not be able to do that. So the question is, we have these diagrams that were given, the structure of adenine and the structure of guanine. These are nitrogen bases on the DNA molecule, and we're told that this is how the cisplatin binds to the DNA. So it binds to the DNA through 2 bases. So the platinum part binds with 2 of the bases, and this interferes with the replication of the DNA, so the cells cannot replicate themselves. So this works in 3 steps. Slow substitution of 1 chloride ligand by water. This water ligand is easily displaced by guanine or adenine in the DNA. Finally, the second chloride ligand is displaced by a different guanine or adenine from a different part of the strand. So we need the platinum to bind to 2 different nitrogen bases on the DNA. First of all, write the balanced equation for step 1. What is step 1? Substitution of one of the chlorides by water. So we're starting with this cisplatin, which is platinum with 2 ammonia and 2 chlorines, and we're substituting it with water. So this is the kind of complex that we will have, and we're removing 1 chloride ligand. So this is our product. Okay, platinum, 2 ammonia. Now we're going to remove one of the chlorines, put instead of it 1 water ligand. I'm left with only 1 chlorine, and the other chloride is displaced. Describe how guanine and adenine can bind to the platinum. If you look at guanine and adenine, these are what we call nitrogen bases. So they have nitrogen on them. And of course, in order to bind to the guanine or adenine, in order to bind to the platinum, the lone pair of electrons on the nitrogen are used to form dative bonds with the platinum. Transplatin binds to DNA, so just why this does not damage the DNA. The problem with, we said the cis works because both chlorines on the platinum are displaced by the two nitrogen bases on the DNA. But the two chlorines are far away from each other. So the problem is that in the transplatin, it can form only one bond with DNA, and this does not affect the replication of the DNA, while the cisplatin has to form two bonds. So for the trans, the second chloride on the trans is far away from the opposite strand of the DNA, so it cannot bind to another guanine or adenine. So it binds with only one, and that does not destroy the DNA. Okay, Reinach salt has this formula. The anion exists as a trans isomer. It contains these percentages, and we're required to calculate what is X, Y, and Z. So this is what we have. This is basically calculation of empirical formula. So we have the percentages. We divide by the mass numbers of each one. The numbers that come out, we divide by the smallest. So this is the basic ratios between them. And we need to use this to get what is X, what is Y, and what is Z. Of course, this chromium is 1, that's okay. Sulfur is 4, and if we look at the molecule SCNX, so if X is 4, then the sulfur is 4. So that means that my X is 4. Now, the Z is what we have for the water. So that is the same as the oxygen. The Z is 1. That means that is because the oxygen is 1. Now, nitrogen, we have other nitrogens other than the ammonia. Now, the Y is for the ammonia. But how many nitrogens do I have in the ammonia? We already have one nitrogen in the NH4. We have SCN. We decided X is 4. So that means we have 4 nitrogens in there plus the one in the NH4. That means we already have 5 nitrogens. So if we calculated that the ratio of nitrogen is 7, then Y is the rest of the 5. Okay, so that is 2. Draw a diagram of the anion. This was the molecule. Where is the anion? Showing its 3-dimensional shape. This is the anion part. So, of course, this is chromium with, we decided that X is 4 and the Y is 2. So that means that we're drawing this kind of diagram in which the chromium is complexed with 4 SCN ligands and 2 NH3s, and we have an overall of 1 negative charge because this is bonded originally to NH4 plus, so the anion alone has 1 negative on it. Explain why the tetrahedral complex exists as 2 optical isomers. So if we have this complex, why do we have 2 optical isomers? We have optical isomers if there is a chiral center. We have a chiral center when we have the cobalt bonded to 4 different ligands, and that means that we are going to have 2 non-superimposable mirror images. This is what we mean by 2 optical isomers. So this is because the cobalt is bonded to 4 different ligands, and that means it's a chiral center, and it would have 2 superimposable mirror images. So complete the diagram showing the 2 optical isomers. If we draw one, the other one must be the mirror image of it. So if this is one arrangement, I can draw the mirror image of that, that would be the other optical isomer. And that's the end of the paper. I hope this was useful to you. I hope you understood the explanation, and thank you for listening, and good luck in your exams.